We would now like to move ahead with our technical presentation part. I'm happy that Danny Molyneux agreed to join this session as moderator again. He was the session chair for the technical presentation part for our first VPS already. Danny is chair of the Young Pipeline Professionals Europe and technical advisor for Quest Integrity. He has a Master of Chemistry from the University of Aberdeen with first-class honors. Danny, thank you very much for joining us again. Please, the floor is yours.
Thank you very much, Dennis, for inviting me back to reprise my role of moderator for this second Virtual Pipeline Summit. I also wanted to take this opportunity to thank the EITEP Institute for all the support of young pipeliners all over the world. We really appreciate it. By now, we are all experienced with online conferencing compared to back at the first VPS in June. So I'm expecting a lot of engagement from the audience today. Please type your questions or comments at any time during the presentations. Our first presenter today is Rene Landstorfer, Operations Manager with GOTTSBERG Leak Detection in Germany. Rene will present a research case study in detecting illegal tappings. GLD started a research project together with another service company and 2 pipeline operators with the aim of simulating different siphoning possibilities along a line. The presentation will cover the test setup, as well as the results of the leak detection run. It will show different leak signatures in the data related to the several test settings and give an outlook on the abilities of the system. Rene, over to you, sir.
Yes. Hello, everybody. I'll just start sharing my screen. And now you should be able to see my presentation. So I hope everything works. Yes, welcome everybody, and thank you for joining my presentation here at the Virtual Pipeline Summit. The presentation deals with, who would have guessed it, illegal tappings. So it is a research case study. What we have done after a short introduction, I will let you know about some project setups and the project data, then about the run results, and at the end I'll give you or show you some examples about illegal tappings we have found in the past with our system, with our tools. And the first question was, is it an increasing or decreasing problem? That has already been discussed in the sessions before. What I have here is a graph from the Concava report of 2018, and it shows clearly that after a peak in the theft-related events, it's a decreasing problem at the moment. That comes from all the efforts the pipeline operators have been taken to deal with that problem. But if you look at the next slide, which is also a graph from Concava report, you can see that all the non-related or non-theft related events have decreased significantly as well. And over the last years, the main reason for spillages along pipelines in Europe is theft, or at least theft attempt. And that leads to the conclusion that there is still a lot to do to avoid these problems and to deal with them. So what we have done was a pipeline run. We are producing leak detection pigs. And it was a pipeline run where we worked close together with the pipeline operator Slovnaft from Slovakia and the service provider, which is also our area representative, Intec. They had been planning and the setup for the trial run, also the locations and installations they have used, and we have been involved in that, but without knowing about the location of the leakages, for example, also the number of leakages and the different test setups. So what we have chosen for the run was a 100-kilometer diesel line in Slovakia, and 3 different leakage setups had been installed along the line. From our side, we used our leak detection equipment, the GLD 202 leak detector in combination with the GLD 303 chassis. These tools are especially developed to detect very small leakages. In fact, we have a certification from the German TÜV for a smallest detectable leak rate of around 6.8 liters per hour. That was during the tests, that was a leak size of only 0.2 millimeters. So it's more or less just dropping out of the pipeline. And these tools are widely used as an addition for permanent monitoring systems, because these are not capable of finding very small leakages during the normal pipeline operation. That's why many operators have their permanent monitoring systems. And in addition to that, for the small or pinhole leakages, they are using our leak detection pigs. So for the trial run, as mentioned, we had 3 different leakage or hot tapping setups. The first one was in a small valve station. It was a DN80 branch with a ball valve, then a 2-meter long DN50 pipe, and at the end of that pipe, a DN15 ball valve again that could control the leak flow, which was around 1.3 cubic meters per hour, equivalent to 16.7 liters per minute. The next picture shows our leak detection evaluation. At that point, we could detect the leakage. I'll just switch to a pointer to give you a better idea on what we are doing here. So the software displays our data. We are recording all the noises in the pipeline, afterwards doing a frequency analysis to make precise statements about the origin of any noise. We are starting here with the very low frequent noises at the bottom left of the screen, and then it goes frequency-wise upwards to the high frequencies at the bottom right. So the green beams are high frequent noises. And what we are expecting from a leak, or what we are searching for, is the noise of cavitation. When the pressurized liquid expands to the outside of the pipeline, it produces these small cavitation bubbles. And as these are imploding, they are producing a certain noise that is in the high frequency range. So if we find a signal that has mainly high frequency signals, then we have an option here to take a look at the signal geometry. We can see the loudness and how the loudness behaved during the signal on the top of that window. And if we find something similar to what is displayed here, then we can be sure that there is a leakage. Additionally, we have the locating feature. What you can hardly see here behind that sign that says Molch is a small hut where the valve is inside and where the installation was mounted to the pipeline. And that spot here would be the location as it was found by our tool, which is already pretty close to the actual spot, around 5 meters. And this is one of the features of our tool, because we can locate during the first run. So there's no need to rerun the tool or to do several runs to get closer to the actual spot. That is already done within the first run. Our next leakage was, I just need to switch off the laser pointer. Our next leakage was in the field. There was a construction site at the pipeline, and there a leak has been simulated by welding a branch of DN25 to the line. Then they drilled with a 6 millimeter drill into the pipe wall, and the intention was to simulate a crack by stopping the drill exactly at that point where the first small leakage occurs. So at that moment where the first high frequency sounds occurred. The leak flow in that case was around 0.5 cubic meters per hour, and that was around 9.5 liters per minute. And if we take a look at the software, at our data evaluation, you can again see clearly, again, we have those high frequency signals from the cavitation. Then the signal geometry and the loudness and some other features will give us a clear idea that this is a leak, and also helps us to avoid false alarms, because we can distinguish between those leak sounds and perhaps some high frequency noises that are only harmonics of other noises next to the pipeline. So, for example, the excavator next to the pipeline would produce a completely different signal than a leakage, even though it has some high frequency harmonics in the noise. So we could clearly detect the leak here. Again, we had a pretty good location feature. Of course, you cannot see the construction site here on the Microsoft Bing map because these pictures are, of course, not updated daily. Then we can move on to our third leakage setup. This was one which can be found very often in these cases. It was again a DN25 welded branch with a ball valve, 6mm drill again, but this time through the whole pipe wall. And to that ball valve, a 20-meter long pressure hose was mounted. At the end, again, a valve to regulate the leak flow, which was again 1.3 cubic meters per hour. That was, in that case, 23 liters per minute. And that is something that is found pretty often, that you have drilling into the pipeline and then a hose of different lengths attached to it to siphon the product, perhaps even far away from the pipeline. And in that case, you can see that the whole signal has significantly changed. We have again some high frequency noises, the green beams. Then we can see the signal geometry and the loudness of the signal. And as you can see here, it's pretty different to the last leakage, for example. Way more quiet. Everything looks a bit different, but still gives us a good idea on what happened here. So it's still clearly a leakage signal. The difference in the loudness mainly comes here from the pressure in the line. In that case, it was around 9 bars in the line. If I switch back to the last leakage, it was about 23 bar, and that makes a big difference for the physics of these cavitation bubbles. So the signal is way more quiet, but still clearly can be detected as a leakage. Again, the location feature was pretty precise at that point. It was also a construction site. So at the end of these trials, we had a good idea on how the leakages change, how the frequencies slightly change from one setup to the other, how the noise loudness changes from one setup to the other, and we could clearly detect all of the 3 leakages. So all in all, it was a successful trial, and we now have a little bit better idea on how the noises behave in the field. So what you can see now are some other examples on leakages or hot tapping spots we have detected in the past. This one, for example, was in Germany, and two holes had been drilled, both around 3 mm in size, and these two led into one pressure hose that went through the field for about 20 to 30 meters to a road where the criminals could siphon the product into a tank truck, for example. And that is also a widely used way to steal product. They are drilling more small holes instead of one big hole to avoid being detected, for example, by intelligent pigging. They try to stay below the threshold of different leak detection methods to avoid being caught. The next one is a slightly bigger hole. This was around 2 centimeters, and they used an already existing construction site where the pipeline, a part of the pipeline was changed. And they just covered the spot where they had drilled the pipeline during the days, and then digged it up at night to steal some product. The third one was in Southern Europe, where we did a regular leak detection run with our tool and detected a leak. So we had a leak alarm. An intervention team had been sent out to the line, and they discovered a hose coming out of the ground at the location we detected. And this one was around 600 meters in length, leading to a place in the woods, which was covered by trees, so you could not detect anything from the by a drone or helicopter at that point. And that was the place where they siphoned the product into a truck to steal it and bring it away. And that is already the end of my presentation. Please feel free to ask any questions.
Thank you very much, Rene. Great presentation. I'm delighted to see so many good questions coming in already. So I'll pose a few of those to you now. We have one from Michael Shora, who asked, we have found found and reported during our corrosion inspection, drilled holes with diameters of 2 to 5 millimeters diameter and a 1/2-inch pipe installed over it for product collection and transport. Could this be detected as well, considering the comparative small diameter?
Yes, this could be. It doesn't matter the diameter of the pipeline and the diameter of the hole. Normally, it doesn't affect the leak detection abilities, mainly because it's nearly impossible to drill such small holes that they cannot be detected by our system. As mentioned before, the smallest leak rate that test with the German TÜV was a leak size of only 0.2 millimeters. It depends a little bit on the pressure of the pipeline, and but in general, 2 to 5 millimeters are no problem.
Perfect, thank you. One from Heinz Watzke here. He says the only disadvantage is that your system functions only when product is taken. When valves are closed, there's no indication of location.
That is true. That's the drawback of the system. As mentioned in the beginning, the tools are often used in addition to permanent monitoring systems. And of course, these permanent systems, they give a permanent overview, but cannot detect the small leakages during operation. Whereas we do not have a permanent overview, but can find even the smallest leaks. For the detection of illegal tappings, one thing that has been successful in the past is do a rerun very frequently. So you could easily run the tool, then take it out, just download the data and restart the run. So there's not much effort needed to run that tool, more comparable to something like a cleaning pig than to other, let's say, MFL or UT tools. So it's pretty easy to rerun, and we had some success by rerunning the tool very frequently.
Makes sense, thank you. Another question from Louis Kabirua, who says, what technical considerations should be taken into account when selecting a leak detection system?
Well, Mainly, I would say how small the leakage can be. So as always, every technology has its benefits and drawbacks. So at the end, it will probably be a connection. It will probably be a connection of different technologies to get the best out of all of them.
Makes sense. Thank you. And specifically for your system, Juan David Betancura asks, which are the requirements of current and voltage?
Current and voltage, sorry. So I did not get that question.
Yeah, he asks what the requirements for current and voltage are. If that's not...
So perhaps we can talk about that in the chat later, and he can explain the questions, because current and voltage is it's a free floating tool. So there is not really, it's like a normal PIC. So there is no need to have something to do with the pipeline.
Makes sense. Thank you. And one final question from Edward Tapanesa. He asks, what are the frequencies of interest that you scan for?
The frequencies are ranging from around 5 kilohertz with the lowest, up to, depending on the medium, depending on the leak geometry, also a crack would produce other frequencies than a drilled hole, for example. But the main range is around 5 to 50 kilohertz. It changes for gas pipelines, then the frequencies are higher, up to 100, 120 kilohertz. But for liquid pipelines, or for, let's say, product pipelines, which are mainly affected by these illegal tappings, the frequency range would be between 5 and 50 kilohertz.
Perfect. Thank you very much. Well, Rene, thanks again for the great presentation.
Thank you for listening.